Chapter 8 Confidence Interval Estimation. Introduction. The following is a general example of sampling a population. Mail-order companies have accounts with thousands of customers. The company wants to deduct the average time it takes for customers to pay their bills, so that it randomly samples a small number of its customers. Look at how long it takes this customer to pay their bills, and draw conclusions about the entire customer population. In the example, the amount per meter is the average length of time it takes customers to pay their invoice. True value can be found simply by studying how long it took each customer in an entire population to pay his bill. This is not really possible, given the large number of customers. Therefore, the firms in this example tend to select random samples and base their estimates on unknown population parameters on the sample data. Sampling distribution. In the sampling distribution, there are two formulas. The first is typical form of confidence interval formula and standardized z-value formula. The t-distribution. The t-distribution, the formula is standardized value. And then other sampling distribution. The t-distribution, a cos relative of the normal distribution, is used to convey population mean when the population standard deviation is unknown. You will see another context in which the t-distribution occurs. The theme is always the same, one way or more interesting, and one or more standard deviation is unknown. Confidence interval for a mean. We will now discuss using the property of the sampling distribution to construct confidence intervals. We assume that the data has been generated by some random mechanism, either by observing a random sample of several populations or by conducting randomized experiments. Its purpose is to infer the value of one or more population parameters, such as the mean, standard deviation, or proportion from the sample data. For each of these parameters, you use the data to calculate a point estimate, which can be considered the best case for the unknown parameter. You then calculate a confidence interval around the point estimate to gauge its accuracy. Confidence interval will increase when you ask for higher confidence levels, but they tend to decrease when you use large sample size. Confidence interval for a total. An auditor may be more interested in the total amount of all receivables added up across all accounts than in estimating the average amount of receivables per account. This section provides point estimates and confidence interval for the total population. The first formula is point estimate for population total, and the second is mean and standard error of point estimate for population total, and the third is approximate standard error of point estimate for population total. Confidence interval for a proportion. How often have you heard on the evening news a survey ending such as 52% of the public agree with the president's handling of the economy, with a sampling errors of plus or minus 3%? Surveys are often used to estimate proportions, such as the proportion of the public who agree with the president's handling of the economy. We will now discuss how to form a confidence interval for any population proportion. The basic procedure is very similar to the procedure for a population mean. It requires a point estimate the standard errors of this point estimate, and a multiple that depends on the confidence level. The first formula is standard error of sample proportions, and the second is confidence interval for a proportion formula.
Interval for a standard deviation. The appropriate sampling distribution is a Rayleigh distribution called chi-square distribution. Tables of the chi-square distribution for selected degrees of freedom appear in many statistics books, but the necessary information can be obtained more easily with Excel's chi-distribution and chi-inverse function. This function returns the probability to the right of value v when the degrees of freedom parameter is df. Similarly, the chi-inverse function takes the form. This returns the value with probability p to the right of it when the degrees of freedom parameter is df. Excel note: if your Excel is Excel 2010, this chi-square word change. There are now chi-sq.distribution and chi-sq.inverse function for the left tails, and the chi-sq.distribution has a last-come argument just like norm.distribution and t.distribution. Also, there are two functions chi-sq.distribution.rt and chi-sq.inverse.rt for right tails. Confidence interval for the difference between means. Independent samples. The framework for this situation is the following. The population means are mu1 and mu2, and the population standard deviations are sigma 1 and sigma 2. We take random samples of size n1 and n2 from the population to estimate the difference between means mu1 minus mu2. A point estimate of this difference is the natural one, the difference between means x1 minus x2. Then an estimate of this common standard deviation is provided by the pooled estimate from both samples labeled as P. Then the standard error of x1 minus x2 is given by equation 8.14. Paired samples. When the samples to be compared are paired in some natural way, such as a pretest and posttest for each person or husband-wife pairs, there is a more appropriate from the analysis than the two-sample procedure. There is likely to be a fairly strong correlation between the pretest and posttest scores. The procedure itself is very straightforward. It does not directly analyze two paired variables. It analyzes their difference. Confidence interval for the difference between proportions. The final confidence interval we examine is a confidence interval for the difference between two population proportions. Therefore, a confidence interval for P1 minus P2 is given by expression 8.15. Here, the z multiple is the usual value from the standard normal distribution that cuts off the appropriate probability in each tail. Also, the standard error of p hat 1 minus p hat 2 is given by equation. Sample size selection. Confidence interval are a function of three things. 1. The data in the sample. Second, the confidence level, and 3. The sample size. We briefly discussed the role of the first two in terms of their effect on confidence interval length and discuss the effect of sample size in more depth. The confidence level has a clear effect of confidence interval length. As the confidence level increases, the length of the confidence interval increases as well. Because each confidence interval discussed so far is a point estimate plus or minus some quantity, we focus on the plus or minus part called the half-leg of the interval. Sample size selection for estimation for the mean. The resulting sample size formula is given in equation 8.17. This formula generally results in a non-integer value of n, in which case the practice is to round n up to the next larger integer. With this sample size selection for estimation of other parameters. We discuss three other parameters in this section: a proportion, the difference between two means, and the difference between two proportions. There are 2 points worth mentioning. First, the confidence interval for the difference between means uses a t-multiple. As was done the mean, this can be replaced by a z-multiple, which is perfectly acceptable in most situations. Second, the confidence intervals for difference between means or proportion require to sample size 1 for each sample. The formula below assumes that each sample uses the same sample size denoted by n. The sample size formula for a proportion P is given by equation 8.18. The sample size formula for the difference between means is given by equation 8.19. Here, sigma estimation is an estimate of the standard deviation of each population where we assume that the two populations have a common standard deviation sigma. Finally, the sample size formula for the difference between populations is given by equation 8.20. Thank you.